Yeah.
Yeah. Okay.
Okay.
Good morning for everyone. Today we have Professor Eduardo Guendelman from Ben Gurion University of the Negev. Okay. Can you hear me?
Mhm.
Yes.
Yes.
Yes, you can hear me. Okay. Okay. Then Professor Gendelman is a professor, emeritus professor in the Department of Physics at the Ben Gurion University and director of the Bahamas Advanced Study Institute and Conferences. Born in Chile, and he completed his undergraduate studies at the University of Chile and obtained his PhD in the MIT under the supervision of Alan Guth, a pioneer in cosmic inflation. He has made significant contributions in the areas such as inflationary cosmology, cosmological constant, and unification of dark matter and dark energy, okay, through modified mature theories. His work includes more than 400 scientific publications and has been widely cited in the academic community. Thank you very much, Professor, for accepting the invitation, and you have the word now.
Okay. Thank you very much. I'm very pleased to be again in contact with the Universidad de Tarapacá in Arica with my friends and students. So I'm going to tell you about linearity in vacuum type black holes. So this is a very puzzling subject because how can you find in such a nonlinear theory, how is it that you find in any case linearity? So general relativity is a highly nonlinear theory, but surprisingly, there is a set of very important solutions that we call vacuum type black holes, which include Schwarzschild, Riccian-Orson, hedgehog black holes, and few others which can be superposed linearly. We explain this linearity. Well, there is an explanation in terms of symmetries and other explanation, but we will focus more on the applications. So the first example is that we study a solution that we after will show that we can superpose to other solutions is the gravitational field of a hedgehog. Yeah, and then the second part, evolution of vacuum bubbles, this I will not touch because we are going to focus just on the linearity, the superposition of solutions. So the gravitational field of a spherically symmetric hedgehog configuration in scalar theories with global SO3 theory is studied in the limit which these models become nonlinear sigma models. The same gravitational effect can be generated by a set of cosmic strings that are all emerging from some central point, and this constitutes a hedgehog of strings. When the hedgehog becomes very strong, the character of the solution changes, becomes a cosmology. Okay, so what is such a solution? We have a scalar field with three components, right? And a potential for the scalar fields that determined by equation 1, where we set the lambda goes to infinity, and then we set if lambda set to infinity is equivalent to the kinetic term, right? We just keep the kinetic term because this in parentheses here becomes 0. Is constrained by the length of this scalar field equals to v squared, right? Something like that. We will see that for small values of v squared, this is a static solution. But for bigger value, it becomes a cosmological solution. Okay, sometimes people call this a defect. This is called global monopole. It's not to be confused with the, because these gauge fields, these scalar fields are not gauged. It's a global monopole. Okay, so we do something here that we correlate the direction of the components in the scalar field space with with directions in physical space. So the scalar field can point in the direction of unit vector r or the opposite. This gives the same energy momentum tensor. And r is the unit vector. So R1 is sinus theta cosinus phi, R2 is sinus theta sinus phi, and R3 is cosinus theta, right? Sounds like. Okay. And then we look at the solution of a scalar field equation coupled to gravity, right? We find, we call the G00 minus A, the GRR B, and then this spherically symmetric R squared times the d theta squared plus sine squared theta d phi, all right? So the energy momentum tensor is given by equation 5, right? And if we calculate, we insert this proposal for the scalar field into this energy momentum tensor, we get that T00, 0 with the index up 0 and 0 with the index down 0 equals TRR equals minus V squared divided by R squared. And then the T phi phi and T theta theta are equal to 0. And all other components are equal to 0. This is very important. What characterizes this set of solutions that we will call vacuum black hole is that they satisfy this equation. So we will see. Once you have this equation and then you have another solution that satisfies the same equation, it turns out that you can actually superpose them. Okay. Yes. And so at the center of the geometry, there is still like kind of a singularity because the scalar field are all emerging from this. This is because this is just because we are taking lambda going to infinity. So if lambda is big but not infinite, all this the singularity is regularized except for a very small, yeah. But then all the fields are okay, and there is a very small region where this solution for the scalar field is not valid. It's modified a little bit because you are not taking lambda going to infinity. So the Einstein equation, right? The Einstein tensor in the left-hand side equals the source 8 pi g t mu nu. And then if we insert this form of the metric, right, with A equals m and B equals m to the minus 1, we find that T00 equals TRR equals m minus 1 divided by 8 pi g r squared. And then you can see that we had also an expression from the calculation, right, of the energy momentum tensor from the scalar field. This relates m minus 1 to the value of the scalar field, right? Maybe we can go back. You see, equation 7 gives us the T00, and then we had also the equation 6 that relates this is V squared, right, is related to this m minus 1, right? This is clear, right? So we have an expression of m minus 1 in terms of the metric. So the metric is determined by m minus 1 determined by phi. Okay. So now we go to the superposition. We take now a metric, right? Generic metric, where the G00, right? G00 is minus A, the GRR is opposite of this. We put in the Einstein equation, and then we calculate the components of Einstein tensor, right? G00 equals GRR, so it happens, right? So that this gives you automatically that the T00 equals to the TRR, with one index up, one index down. So this is exactly the same thing. And we see that there are no nonlinear terms. Everything, all the components of the Einstein tensor are linear in A minus 1, right? So you see, here's A minus 1. This is the derivative of A minus 1 because derivative of 1 is 0, right? So you see that the derivatives of everything is linear in terms of A minus 1. Okay? And if T mu nu is a function of R alone and not A, so you see that you can get, you can put another solution that is also satisfying the T00 equals TRR, and you can just superpose them, right? Something like this. For example, you can, to the hedgehog, you can superpose a Schwarzschild solution, and you can, so you have a superposition principle. Although the general relativity is extremely nonlinear, when you constrain yourself to this inverse type of matrix, you can actually superpose solutions, right? You know, for example, the Schwarzschild solution has this feature, right? That you have here the G00 and the GRR is the inverse, right? And then this is the matrix form. You can, well, this is the calculation of Christoffel symbols. So you can superpose, for example, a cosmological constant. The cosmological constant is 1 minus chi square r square. You can superpose to the hedgehog, which gives you m, and you can superpose to Schwarzschild, right? So it's, for example, if you superpose these three types of solutions, you get a generic form for A, which is the G00, m minus 2gm, I by r, chi square r square. And B is the inverse, right? Something like that, right? B is the GRR. If m is a constant, say m is a constant less than 1, generically, right? But it can become negative, right? This, right? If you see, if it becomes negative, if it becomes negative, A is totally negative, because m, you remember, it was like 1 minus v squared, right? So if v squared is become big, more than 1 in a Planck units, right? I just said it in Planck units. M is become negative, and this becomes like the time, the real time is R. R is the time everywhere for big M. In the Schwarzschild solution, you know that inside the horizon, the R is time, and outside is T. But here, if M is big, everywhere R is the time, and time is always a special coordinate, right? Something like this. So M is positive, or if space-time, yeah. Okay, and then there is a place where A equals 0 are certain value, and this is what we call a horizon, right? But if M is negative, R is always a time-like variable. It has to be interpreted now as an anisotropic cosmological solution, right? And then you can do a gravitational field of instead of thinking of a scalar field, you think of a bunch of strings emanating from the origin, right? And then a star, for example, and this is what we call a hedgehog of a string hedgehog configuration. For a simple cosmic string, it could be, some people say, took this idea, it doesn't have to be cosmic string, it could be the string from string theory. But okay, never mind. The string is characterized such that the T00 equals to, I mean, suppose that we have a string in the direction of the z-axis, right? So it's localized around the z-axis, so we have to put the delta of x times delta of y, right? And T00 is equal to TZZ, right? And then we have this, and then we consider a bunch of strings emanating from the origin. So we will get a string hedgehog, and then we replace just it's not just the x-axis, it's a bunch of strings, and then we have this condition, right? T00 equals TRR. And then we get, and then the string doesn't have components in the theta energy momentum tensor, doesn't have components in theta and phi. So it becomes, from the point of view of the Einstein equation, it becomes the same as what we did before for the scalar field. So the solution is the same. It's G00 is minus m, some constant here. GRR is m to the minus 1, right? And this is the solution, right? Something like this. You can, if m is positive, right? If m is positive, you can redefine time, and then you define a t bar as a square root of mt. And then you can redefine r, and then you have this, right? But then you have to redefine also the angle. Yeah, but if you redefine the angle, this changes the periodicity. So this is what's called a conic singularity, right? The space is locally flat everywhere, but it's a conic singularity because you don't go from 0 to 2 pi. So this is the famous conic singularity. Anyway, this solution we found it with my colleague Rabinovich, right? But it has been generalized by this fellow Hedrick, right? And then he takes TTT and TRR and all the other components like TR or RT and all the angles equal to 0. And then he finds in d dimension, here is not the solid angle in 2 dimensions, it's solid angles in p dimension. And it still satisfies this f of r dt squared plus f of r to the minus 1, r squared the omega squared. And the solution for f is like he likes anti-de Sitter because he's a string theory, and the string theory like more anti-de Sitter rather than de Sitter. So he is the r squared, right? Is normalized to 1, this cosmological, the negative cosmological constant, plus 1. Then if p equals 2, this is what we did in 4 dimensions, right? The angles, there are 2 angles, p equals 2, you see that this is a constant, right? So that's what they have here. now is a generalization of Schwarzschild, right? It's anti-de Sitter Schwarzschild solution. And what it used to be mass divided by R, if you have p dimensions, is mass divided by p minus 1, right? Something like that. Okay. So that's the hedgehog black hole in d dimensions. Okay, and then there is a once you know that it's an inverse metric, you know that the G00 you can take it from a Newtonian argument, right? Because you know that the G00 is related to the Newtonian potential. You do the same argument, and then you find the correct result. Okay. So this is the what I said, that you had to you can superpose hedgehog, Schwarzschild, and a cosmological constant, right? And if m is negative, this solution becomes a cosmological solution. Somebody else, there is a physicist, there is a gravitational fellow called Ted Jacobson, right? He worried about, he had good arguments. Yeah, we discussed with him. He acknowledged our discussion. He had a discussion of why GTT times GRR equals -1. He said that so many cases this happens, right? The GTT times GRR equals -1, right? As he reviews here in his abstract, the Schwarzschild solution, Reiser-Nordström solution, Reiser-Nordström's de Sitter solution, generalizations, right? And then he says that these vacuum solutions are the thing that is special about this vacuum solution is that the energy momentum tensor is proportional. He said it here, is proportional to the metric in the TR subspace, right? So he shows that this condition holds. If this condition holds, he gets the inverse metric, right? That the GTT is inverse to the GRR. Okay, he got the examples. So as he said, we call a vacuum solution where T mu nu is proportional to G mu nu, right? This is a cosmological constant because the proportionality constant must be a constant because of conservation of energy momentum. If they are proportional, the proportionality constant has to be a constant, right? By the energy momentum conservation. Now we define a vacuum black hole as something that is similar to this, but this is too restrictive. If we just say this, right, that T mu nu is proportional to G mu nu, this just gives us a cosmological constant. So we have to be a little bit, we can still call it vacuum black holes, but we say that this holds this as Jacobson says, right? That this holds, but only in the TR space, right? So if we raise the one index up here, right? This says that T mu nu with one index up and the other down. It says that the T mu nu, one up, one down, is a delta, right? A delta Kronecker, right? So that means that in the subspace of TR, we get that we have the T rho mu has to be proportional to the identity matrix in this TR space, right? Right. something else can happen in the theta phi space, right? Something like that. So we must have our definition of a vacuum black hole is this, right? And the mixed components like TR or RT is zero, right? Because it says this identity matrix. And then, yeah, and then we don't say in the meantime about T theta theta, T phi phi, all that stuff. Yeah. So he has a nice argument. He says, suppose that the metric is given by f of r dt minus f of r dt, gr dr, and r squared, hij dxi dxj. So he doesn't even restrict himself to 4 dimensions. This can be d dimensions, and these are d minus 2 angles, right? Angles. So you see that but we know that in the so now we know that in the subspace T R the metric the metric is proportional to the space-time metric. Now he says, let's consider radial null vectors in the radial direction, right? So if you calculate radial null vectors in the radial direction, the component L mu, L of t is g square root of g, Lr is plus minus f of t, and Li is 0 because it doesn't, it's radial, right? Off diagonal component Tr vanish because we have a time reflection symmetry. And then I calculate here R mu nu, L mu L nu. And if I use these results, right, for this, is G T T, G R T T plus F R R R. And then this gives us, by using the expression for the curvature, Ricci curvature is equals to d minus 2. The derivative with respect to r of f times g divided by f 2rg. But this we know has to vanish because we are calculating el mu, right? This is, well, because we said that the r mu nu is proportional to g mu nu. So this is the like inner product of this light tensor. So it has to be 0. So it can be 0 only if f times g is a constant. And then by rescaling the time component, we can also get that that f times g is equal to 1. So the force velocity of a radial null curve is like this, T of L, R of L. So it's K mu T dot R dot, right? And then we have that this is a null vector, so we have this, right? Something like this. And okay, and then he says that the translation symmetry gives us an energy conservation, right? And this gives us that the fg square root of fg times r dot is a constant, but since fg is a constant, this means that the r dot is a constant, so that means that the r is a linearly related to the affine parameter, so it's also an affine parameter. Okay, then he has an argument with the Ricciardori equation. The Ricciardori equation is this, right? Well, theta is the derivative of the logarithm of the area of a transverse element. And then he gets basically this equation. but the R, we agree that the R mu is 0. So again, you get that this is a R is a fine parameter because the second derivative with respect to a fine parameter is a constant. Okay, these are nice arguments by, yeah, I found this a nice paper that is interesting because it illustrates some class of black holes, right? Where you can superpose because they give you the inverse form, right? Okay. So he finds this Marcelo Salgado finds that under certain circumstances imposed on the energy momentum tensor, a theorem that characterizes a two-parameter family of static spherically symmetric solution to Einstein field equation, black hole is proved. A discussion on the asymptotic regularity and the energy condition is provided. Example that includes the best known exact solution with these symmetries are considered a trivial extension of the theorem which includes a cosmological constant he discussed, right? So you see he has a metric, right? MGAB, he says the metric, right? M is a manifold, right? We satisfy the Einstein equation. The G00 is n squared, right? Something like this. Minus n squared. The GRR is a squared, and then this the angular part, right? Is in 4 dimension. You have two angles, right? Theta square, theta and sinus theta, right? And we get to our favorite condition, right? Something like this, right? That TT equals TRR. And then he imposes some condition on the angles, the angular part of the energy momentum tensor. So let's say that the angles are the T theta theta and the TRR are related by a constant, right? A constant, right? So he finds the general solution, right? We know that once we have this condition, we know that from what we considered before, and from our argument, from argument of Jacobson, said that we know that the G00, right, has to be inverse to GRR, right? And the G00, there is a equation that one can obtain, right? That is a 1 minus the 2mr divided by r, where m is like the mass inside the radius r, right? Something like this. And we can use that equation. And we get that this has to be the inverse, right? We don't have to calculate this one anymore because the TTT equals TRR implies that the G00 is inverse, right? So he says, right, you have to have M of R can be a constant, right? So the energy momentum tensor is restricted to be of this form, right? Something like this. TAB is equal to diagonal, right? 1, 1. This is equivalent to say that the TTT equals TRR, so that's why we put 1, 1 here. And this is the relation between, sorry, this is the relation is T theta theta equals kappa TRR, right? T theta theta and T phi phi are the same because, right? Because by a spherical symmetry, right? Otherwise we violate spherical symmetry. So we have this condition here, right? Something like this. Yeah. So we have m. So in this case, the energy momentum, this constant is 0, right? You just have all the mass at the origin, right? It's some function. If this c is not 0, we have m minus 4 pi c r 2 kappa plus 1, right? And then you say that the kappa is not equal to minus 1/2. Yeah. And c is not equal to 0. Okay, so we get this. And if kappa is equal to 1/2, we get this logarithm, right? Because usually when the logarithm is, you see that the logarithm, the exponent becomes 0, but the denominator also becomes 0. So you in this limit gives you a logarithm, right? Something. Okay. So this you put this equation we had already, right? Something like this, right? Yeah, this we had. Yeah, this equation we had here. He's using the, yeah, his equation is linear in a square, so it's a little bit misleading that yeah, but from our point of view, we know that the equation is linear in a square, right? Because our notation was this was the a. We call it a here in our pages before, right? So a square minus, you see that the equations are linear in a square, right? Okay. So when we use this, right, we get that the derivative of m is t equals this is known equation, right? Something like this, from general relativity, spherically symmetric. What is this? Yeah. Okay, so we get this solution that derivative of TRR minus TT, right? We get that this, yeah, we get that this, because we see that here that there is this decoupling, right? Because we have the TTT minus R is, but this is 0 for our case, right? So we know that the derivative of this is 0, so that AN is inverse of A, right? Something like this. Okay, so you consider conservation of energy momentum tensor, and you get basically an equation for the derivative of TRR in terms of TRR, and this is you can integrate, right? And then TRR is equal to C divided by R to the 2 1 minus kappa. Okay, so we got these solutions, right? Something like this, right? Again, right? Okay, so this is an example of inverse metric, right? That is nice. Now there is another particular issue that is very interesting. We discuss here all these issues, that linearity, non-self-interacting, and the spherical equivalence principle and Hamiltonian bubble. What is the, well, we said something about the linearity already. Linearity means some kind of self non-interacting. What is the spherical equivalence principle? Is like, suppose now that you have this space-time, or if you have two space-times of the same sort, but then you are separating them by a domain wall. And the domain wall travels across a spherically symmetric, say, for example, or, yeah, so in a spherically symmetric way. In general case, if you have a surface that is traveling in a medium, right, it will get energy and momentum from the medium. But what is interesting is that for this particular matrix, the medium, the matrix, this energy momentum tensor, they don't exchange energy with this bubble, like as a domain wall or something like that, right? So this is interesting because it allows you to consider brane worlds, right? The idea of brane worlds is that you have in high dimension, right? In brane world, you have a surface that's traveling in a high dimensional space, but the brane world in itself has to be self-consistent, like a closed system, right? Something like this, because suppose that somebody tells you we live in a brane world, right? But then you have to explain why we are not getting energy from the embedding space, right? So that's the idea, right? Something like this. One is one possibility of application, right? And for this inverse matrix, this is this is satisfied, right? Okay. So we say the class for a large class of spherically symmetric gravitational field, matter is dropped in a spherically symmetric way. It is possible to consider these free falling shells and their associated energy momentum tensor as not affected by the environment, right? And then this goes together with non-interacting gravitation fields for this inverse matrix, right? Inverse this particular form of energy momentum tensor. In this case, we consider the membranes to be 2+1 dimensional, but you can generalize to n+1 dimensional, right? So write something like that. Okay, so that's a long abstract. Yeah. If you have a system that is closed, you can define a Hamiltonian, right? Something like that, right? Yeah. So you can Hamiltonian in 2+1 dimension without involving the embedding space. So we go back to this metrics, right? The metrics that go together with the they go together with the T00 equals TRR, right? And as we said, it's known for Schwarzschild, De Sitter, Reiser-Nordstrom, and hedgehog or global monopole, all kinds of things. We will discuss also the non-singular black hole that is constructed in this way, and then we will discuss what can we do. Suppose that there is a shell with a trajectory, a spherical shell with the which is described by R equals R of t. So these shells, or there could be, what is this? Yeah. These shells will be not interact with each other. Well, this is easy because they are separated from there. They don't have the same. But what is interesting, they will not, we require that these are not interacting with the environment. The environment is the energy momentum tensor, right, of the space, right, something like that. Okay. And then we consider a shell, right? It's a shell is described by a 2+1 energy momentum tensor. Usually the energy momentum tensor of the shell has right, is the energy momentum tensor is projected. Yeah, we have the energy momentum tensor. We project into the shell and we integrate over the shell, right? From minus epsilon to epsilon, right? And we take the Gaussian normal coordinates, right? Where the eta measures the geodesic distance in the direction of normal of the wall, right? By definition, eta equals 0 is the location of the wall, right? And n mu is the normal to the wall. So this defines a projector onto the wall, which is h mu nu equals g rho mu minus eta mu eta nu, right? So you see that this projector projects to 0 the vector eta mu, right? So we take from one side of the wall, from a negative side is one side of the wall, from positive side is another side of the wall, and then we say the energy momentum tensor is going to be the contribution to the wall, right? S mu nu delta of eta, right? That's one contribution. And the other contribution is energy momentum tensor T mu nu 1 theta in the side where theta is eta is positive, right? And on the other side, T mu nu 2 of theta of minus theta, right? You know the theta function is 0, right? Is 0 if the argument is negative, right? And is 1 if the argument is positive, right? So this contribution is, it holds for the eta positive, and this contribution holds for eta negative, right? So, okay. Okay, so that's what's happening, and now we demand the energy momentum conservation of this four, right? Something like that, right? So we define the coordinates I on the wall, right? The coordinates, our coordinates are we will be defined by the coordinates on the wall, which are I, theta, phi, and tau. Tau is the proper time measured by an observer at the wall, and then the eta is the we define to define the coordinate of a point outside the wall. We define the eta, right? From we take a geodesic which is perpendicular to the wall and measure the distance, right? And the eta is positive in one side of the wall and negative on the other side. So in terms of this, what's called Gaussian normal coordinates, we have g eta eta with index down equals g eta eta with index up equals 1. They are not mixed coordinates with the mix eta and theta, phi, and tau. Okay, and then we define the what's called the extrinsic curvature. Is the covariant derivative of eta. In the extrinsic curvature, it has the indexes ij, right? Ij is the theta, tau, theta, and phi, right? It's the derivative of the gij with respect to the eta, right? Okay. And then you say something interesting happened with the energy momentum tensor conservation, right? We want energy momentum tensor conservation. If you calculate the energy momentum tensor, the derivative of the divergence of energy momentum right? Component I, you get a bunch of equations, Tij, covariant derivative with respect to the 3 dimensions, right? Then there is a covariant derivative with respect to eta. The extrinsic curvature appears here, right? And then this appears here, right? Tij. And the other contribution is T eta nu. It gives you this something similar, right? With the extrinsic curvature. So if I take the first equation, right? If you take the first equation, you see that you have some derivatives of derivative of delta function here, right? SIN, SI eta, right? And then there's the term proportional to delta function, right? And this term we don't want. We don't want this term proportional to derivative of delta function because it cannot cancel with anything else. So the only possibility is that the SI eta is 0. It's reasonable because that means that there is no momentum, energy momentum component I in the direction eta, because this will bring energy momentum tensor outside of the world, right? Something like that. Okay. So we get sorry, yeah. So we get, as I said, this, right? Something like this. Right? If SI eta is 0, well, you have this 0 and this 0. You have a lot of things 0, right? And then you have this coefficient of delta eta is must be 0, right? So one condition is SI eta equals 0, and the other condition is that this is 0, but this is 0, and this is 0. So we are just left with the non-conservation of energy momentum tensor in the world, because there is energy momentum, there is energy momentum entering the world and leaving the world, right? SI eta minus I eta, and the difference is the non-conservation of the energy momentum tensor in the world. S is the energy momentum conservation in the world. This part is has to be 0 anyway, right? Because we make vanish the delta prime component. Okay. So this we want to see what happened with the second part, right? The non-conservation of energy momentum tensor, right? So this is like right, in an arbitrary coordinate system. This is like Ti eta is, I project the mu into the components of eta mu, right? Something like this, right? And then so, and Tij is this, and then you take care of the other index I with the projector operator on the wall, right? Because the I is something that lives on the wall, right? So this thing here refers to thing projected onto the wall, right? Something. So, and then we don't want to flux from the embedding space, right? That's the idea of having a closed system, right? Something like this. So that means that this projection here, right? This projection here, the energy that goes into the eta direction has to be 0, right? So that was decided, right? Something like this. And we want, we don't care about the difference. We want the flux from one on the other independently to be 0, right? Something like that. And then we get this expression, right? Eta mu is equal to eta mu of this, right? Well, the expression, the conclusion is that this has to satisfy this, right? And then by the by contracting with the eta mu both sides, we get right, and considering that the n mu eta mu equals 1, we get that lambda is equal to this, right? We have this condition with the lambda, which is equal to that. Okay. And this is satisfied, we see that this is satisfied by the case that the energy momentum tensor is TTT equals TRR, and the TTT is equal to, right, T tau, TR and RT equals 0, and all mixed components are 0, right? And the angular components are T phi equals T theta theta, right? Something like this. So so we get, there is an intuitive way of understanding without so many calculations. Is suppose that you are in a flat space, and then you say that you propagate something in the a plane in the x direction, but this plane has the energy momentum tensor in this direction. But if you propagate in this direction, the energy momentum tensor, if you do a boost in the x direction, right, in the x direction, if you do a boost, this is invariant under boost, right, something like this. This you can see easily, right, because yeah. So if this is a way to see that this condition T00 equals TRR is consistent with a domain wall not exchanging energy with the environment, right? Okay. We have a little time to do another subject. Yeah. This is a very interesting paper by Irina Dimnikova. She wants to consider a spherically symmetric vacuum stress energy tensor. This is what she basically agrees that this spherically symmetric vacuum energy condition is T00 equals TRR. But then she wants to get to consider a black hole, and not only do a black hole, but do a black hole which is free of any singularity, right? Something. So, well, she does the calculation of the metric. The metric is this in general. She doesn't assume nothing. But then she takes T00 equals T11, right? T00 equals TRR, right? So the Einstein equations give you the d lambda dr plus d nu dr equals 0. So lambda plus r is equal to f of t. But then you can take lambda plus nu equals 0 because the function f of t you can absorb by redefining the time. And then take a particular expression for this that gives you the non-singular black hole. Yes. T00 equals TRR or T11 is epsilon 0 exponential of r to the cube minus r to the cube divided by some constant, right? Something like this. Yeah. And then we will see what is it. Yeah. So the mass function, right, is as we saw with the Marcelo Salgado, right, the same, is 4 pi divided by c squared integral from 0 to r of t00 r squared. Yeah. If r goes to this r goes to infinity, gives you the total mass connected to the Schwarzschild radius. Schwarzschild, yeah. Okay. And then she says, yeah. And then she calculates the m of r. She gets a function of r divided by r of rg of r divided by r. C squared dt minus dt squared 1 minus r of g, r of g, r of g, r divided by r squared, this is the angular part. And the calculation of this r of r gives you this equation, right? This equation here. Yeah. You see, if r goes to infinity, the exponential you can forget, right? And then you get here you get the r of g divided by r, right? This is the 2gm. Yeah, this is the 2gm. You get the Schwarzschild asymptotically, right? Very quickly goes to Schwarzschild. Yeah. And then, well, this r cube asterisk is defined in this way, right? Something like this. Why? Because now you take the other limit. You take the other limit, r. This is r0 is defined to define is a parameter of the de Sitter space that you get for r small. If you take r very small, you get 1 minus the exponential is also 1, and then you have the first term in the exponential is r cube divided by r star. The one from here and the one from here is they cancel, but then this gives you something r cube, right? But then it's divided by r, so it gives you a de Sitter space in the r very small because you get something quadratic. This becomes cubic, but the divided by r is quadratic, right? Because you divide by r, and so this is the thing. If you take for very big, you get the Schwarzschild, right? And if you get for very small, you get the de Sitter, right? Let's remind.
Professor, sorry. What is a small rg? What is?
It's a small rg is a 2gm,
Ah,
because you see that so in order to get from when r goes to infinity, this is just g, right? Rg. So you want to get the Schwarzschild here. So it's normalized to be 2g m, right? The Rg. Okay.
thank you. Thank you.
And then yeah. Okay. I missed the yeah. So you calculate the energy momentum tensor, right? Let's see. Maybe I missed this page here, right? The T0, the T22, and the T33 are these exponentials, right? Yeah. Well, 1 minus 3 r cubed, yeah. But when it goes to infinity, it goes very fast to infinity. Okay, and then the energy momentum tensor become isotropic when you go to r goes to 0. The t0, 0, and the four components, the t0, 0 equals the t2, 2 equals the t1, 1 equals the 3, 3, 3. Okay. So this is consistent with the de Sitter, right? De Sitter, we said, is a vacuum solution. So for very small, also you get the de Sitter space. For very small r, you get 1 minus r squared divided by r0, the inverse of it, yeah. And then we said for very big, we have this, right? So that's why the answer to your question, this has to be 2gr, the rg, right? It's the Schwarzschild radius, basically, right? Or something. Okay, so it's non-singular in the two limits for r going to 0, you don't get the singularity, you get the Sitter space. And for large radius, you get the Schwarzschild. Okay, so we are almost 1 hour, right? It was supposed to be. So to finish, I put a list of problems for students. So problem 1, well, if they want to solve it, okay. If they don't want to solve it, it's okay. Yeah. So the first problem would be superpose a cosmological constant, right? Because the cosmological constant is one of the solutions that you can superpose, right? According to which, because it satisfies the TTT equals TRR, right? It happens to be that also all the other components are equal, okay? But that you don't need for the superposition. So all the components are equal, right? And equal to, say, lambda, which is a constant. So the problem is superpose this non-singular black hole of Diminikova that we just explained in the page before. And then you get an arbitrary de Sitter or anti-de Sitter. Now the solution can be anti-de Sitter also. Diminikova said de Sitter, but if you superpose to lambda negative enough, you cancel the positive cosmological constant of Diminikova, and then you get the anti-de Sitter space for small r, right? An arbitrary Schwarzschild de Sitter or Schwarzschild anti-de Sitter for big R. Still, you don't have singularity. So other idea is experiment with the more superpositions of inverse metric. Another exercise. Add to 1, that means that the Diminikova, right, plus a cosmological constant, a hedgehog solution, which also satisfies this, right? So the idea is you add a hedgehog solution, right? That the hedgehog solution had this, and all the others were 0, right? All these others were 0. You add to the Diminikova a hedgehog solution, and the hedgehog solution we saw in our transparencies before. If it's strong enough, the radius becomes a time coordinates, right? So going from 0 to r equals 0 to r very large, you are connecting two solutions with the different cosmological constant, right? So because the r is a time lag, it seems like it would be like what is popular now in the universe. You have a period of one cosmological constant, and another, which would be the inflation, and another with what we call the late universe, the late dark energy, right? So this would be some kind of another exercise or something like that, right? And This you do because you convert this, you have this property that you convert the solutions into cosmological constant when you add a strong hedgehog, right? The other problem is that I couldn't get into this, right? Consider thin shells separating two inverse metrics and find the motion of these shells. This is what's called the Israel matching condition, right? So this is an exercise that is very interesting. Okay, so that would be almost 1 hour, right? So more or less the length of a talk. I think.
Uh,
So I say thank you very much for your attention.
Thank you very much, Professor, for your very nice talk. Also, can you share with us these notes to the students before the exercises?
Ah, yeah, I can mail it to you, yeah. And
Okay.
also, yeah.
Thank you, Professor. Does anyone have a question?
Yeah, I got a question for you, Professor.
Yeah.
Can this that how you say Daimilikova? I don't know.
Dominikova, yeah.
Daimilikova.
Is a Russian that works in Poland. Yeah, something like that.
Can this Daimilikova metry be derived semi-classically?
That's
For
interesting.
example,
I
by
think,
including the expecting value of the Timunu.
yeah. It's well, she does it the opposite, right? She assumes the Timunu, right? But yeah, let's see how she does it. Let's see what is it. She assumes this. Yeah, she assumes the Timunu, right?
Yeah.
The only thing is she assumes, yeah, she has an argument that you can get this from particle creation or something. But in her first paper, she does a like she just assumes that to get. There are many people that work on non-singular black holes. They don't have it, so they just assume, right? Because, but yeah, it would be interesting to find. Yeah, I'm not sure there is a derivation of this equation 8. Yeah.
Yeah.
Okay. Thank you, Joelsi. Any other question? Some student? Okay. Okay. Professor, can linearity in this vacuum solution be extended to dynamical or no vacuum scenarios, such as those
Ah,
involving, for example, scalar fields or matter content?
yeah. Well, what happens is that you can make these solutions dynamical
Yes.
by converting the radius into time, something like that. I think this is kind of dynamical, but I don't know if the condition of vacuum is very restrictive. So I don't know if one can do. Once you go to more general, the solution is not. Yeah, I don't know how much dynamics you can do. Yeah, the thing that you can do dynamically is, for example, you put this hedgehog and make the hedgehog very big, and then the radius become, instead of static solution, becomes a cosmological solution. So in a sense, that's dynamics, but more general than that, don't know. Yeah.
Okay.
Well, there was some other papers from some people from Czechia. They call it. They related to this, but this is too much. I didn't go into that. That they call it decoupling. That is kind of generalized. This gravitational decoupling instead of the linearity. And they have examples with a rotating black hole and stuff.
Okay.
There was somebody that was in Chile also, maybe visited you. Some Ovalle, you know him?
Ovalle.
Ovalle, no?
No, no, I don't know. Sorry.
Okay. It visited Antofagasta or something.
Okay. Eh,
So,
yeah,
so I didn't tell you the
Ovalle is between,
everything.
I think Ovalle is is close to Antofagasta, no? Are you speaking about of
No, the name of the
the
person
name
is
of the,
Ovalle.
okay. Okay.
Yeah.
Eh, yes, thank you, Professor.
Okay. So I'll send you the PDF of the talk. Yeah.
Okay.
And then if the student can think about solving maybe one of the problems is can be a paper. I don't know, this one that to turn the Diminikova solution into cosmological solution that connects two different dark energies or whatever. I don't know. Maybe we can write the paper. Okay.
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 Thank you,
So
Professor.
thank you
Uh,
very much.
any other question from the students? Maybe no, but maybe with the exercises, they are going to have some questions. Okay.
Yeah. The exercise we can.
Yes, and then yes, thank you very much, Professor.
Okay. Very good.
And
Thank you
I
very
hope
much.
no, I hope see you in Lima, okay, for the
Yes, of course.
Congress. Okay.
Yeah.
Okay. Thank you very much, Professor. And then
Thank you.
bye
Nice to
bye
talk to you. Bye.
bye
See you.
for
You're
everyone.
welcome.
Okay, thank you.
Thank you.